So it's my pleasure to welcome our speaker today, Jun Le Goh. So he's going to speak on computing descending sequences in linear orderings. And as far as I can see, it's a joint work with Pauli and Manu Valenti. So please, Jun, you have the word.
Thank you. Thank you, Vasco, for the invitation, and thank you all for coming. As Vasco said, this is joint work with Arno and Manliu. Okay, so informally speaking, this is the main question that we will address today. Namely, how hard is it to compute an infinite descending sequence if you're given an ill-founded linear ordering L? Okay, so what do I mean by this question, right? Right now, this is an informal question, so it's not stated in a formal framework. But for example, one thing that we can say right away is that, for example, there are computable ill-founded linear orderings with no hyperarithmetic descending sequences, right? These are known as Harrison orderings. So we know that this question is not going to be too easy, at least, right? So you're not going to be hoping to find an arithmetic descending sequence all the time or anything like that. So that's one possible way in which we can measure the complexity of such a problem. Another thing that we can do is to compare this problem to some other problems that people see as benchmarks. And in this case, there is an obvious problem that we can compare this to. Namely, we can look at the problem of computing a path on an ill-founded subtree of n to the less than n. And it's pretty much immediate that the problem of computing descending sequences reduces to the problem of computing paths as follows. So I want to go through this in detail just to show you how, like, what I mean when I say that there's a reduction, right? So first of all, we are given linear ordering L, okay? And then we can compute the tree of all finite descending sequences in L. Okay, just ordered by extension. So that's a computable procedure. And now in this tree, if we have a path in this tree, then we can go backwards and get an infinite descending sequences in L. So if you have a path P on this tree TL, then we can compute an infinite descending sequence S. And this is also a uniformly computable operation, both forward and backward. So this is what I mean when I say that there is a reduction from this problem of computing descending sequences to the problem of computing paths. And later I'll give a formal definition, but for now I just want to give the motivating examples. Okay, so we have a reduction in one way. So what this says is that this problem is, well, one way to see it is that the problem of computing paths is at least as hard as the problem of computing descending sequences, right? And so the natural question is, how about the other way around, right? If, say, we want to compute a path on a tree, is there some way to reduce this to the problem of computing a descending sequence? Well, there is some kind of reduction. Let's just go through what it is. So given a tree T, we can compute a linear ordering. It's a Kleene-Brouwer ordering, right? So just remind you what it is. If you have two strings in the tree, sigma and tau, sigma is below tau in the Kleene-Brouwer ordering. If either sigma extends tau or sigma is lexicographically below tau. Okay, so that gives us, if you're given a tree, that gives us a linear ordering. And furthermore, we know that if the tree is ill-founded, then the linear ordering we get is also going to be ill-founded. Okay. Now, how about going backward? So what happens if we are given a path? No, sorry, if we're given a descending sequence in the Kleene-Brouwer ordering, how do we get a path on the tree? So we can do this, given a descending sequence sigma I in the Kleene-Brouwer ordering, we can take kind of the coordinate-wise limit, and that will give us a path P. Okay, so this limit exists, right? Because for each coordinate finitely many times, the path might move to the left, but because we are in the natural numbers at each coordinate, so you can only move to the left finitely many times. So this backwards map over here, the map that takes in a descending sequence and gives us a path, that's no longer a computable map, right? That's a limit computable map now. Okay, and that's a less nice situation than before, right? Before we had computable maps going both ways. And so a natural question is, well, can we do better, right? Maybe there is some other kind of ordering that we can consider, which would enable us to have a nicer reduction. Okay, so now I want to give some formal definitions for in order to frame the questions that we are asking in a more precise way. So this will be a short introduction to Weirach reducibility, which is a notion of reducibility between problems, and it's a uniform notion of reduction. So before we talk about the notion of reduction, first we have to formalize what we mean by a problem. So and that's predicated on the notion of a represented space. So if we want to do computation on spaces that are not, say, the natural numbers or the real numbers, we can do so if we know how to kind of encode the objects in the space as a real number, for example. Okay, so like a classic example is say you can code the real numbers by rapidly converging Cauchy sequences, right? So when you compute with reals, really what you're doing is you're computing with these Cauchy sequences. And this allows us to transfer notions of computability from n to the n, bare space, which I accidentally called the reals, but really what I mean is bare space, to X. So formally speaking, a represented space is a pair consisting of X and a mapped delta, where delta is a possibly partial surjection from bare space onto your space X. So this here is the notation for a function which is allowed to be partial. And the point here is that it has to be a surjection because every object in X has to be named by some element of bare space, right? So if it doesn't have a name, right, then we can't talk about it. So this is a term that I will use sometimes. So each element of X is named by some P in n to the n. And I want to point out that multiple names are allowed, right? It doesn't have to be just one name, right? For example, in the Cauchy sequence example I gave just now, a single real can have many, many Cauchy sequences which converge to it. Okay, let's see some examples that we will actually use in our work today. So basic examples, of course, is n to the n itself. And we also have the natural numbers. Since we are talking about descending sequences in linear orderings, we will also care about the space of linear orderings, space of trees, subtrees of n to the less than n. This guy here, so this is the space of pi11 subsets of n, and this here is the space of sigma 11 linear orderings. Okay, so I mean these are just names that I'm going to use, and all of these spaces can be represented in standard ways. So we are not going to explicitly mention how we represent them. You can do it in a bunch of different ways, and they're all equivalent in a certain technical sense. Okay, so now that we have these represented spaces, we can talk about what we mean by a problem. Before that, let's talk about some examples of what we intend to be problems. So of course, the main problem that we care about today is what we call DS, it stands for descending sequence. So you're given an ill-founded linear ordering and you want to produce an infinite descending sequence. Another problem that I already mentioned, so this is the problem of computing paths on ill-founded subtrees. So given an ill-founded subtree of n to the less than n, you want to produce a path. And this is typically known as choice on bare space. So that's why it's written C and N. There's also another problem that we already implicitly mentioned, namely the problem of taking the limit. So this is called lim. And what we're given is we're given a convergent sequence of elements of bare space. And we want to produce the limit of this convergent sequence. So the place that lim appeared is in the when we talked about the Kleene-Brouwer, right? When we have a descending sequence in the Kleene-Brouwer ordering, we took the limit in order to get the path on the original tree. So here are some examples of problems, but formally, what is a problem? It's a multi-valued function between represented spaces. So here, x and y are represented spaces. And this problem is going to be a multi-valued function, and it could be partial as well. So it might be defined only on some members of x. And for each member of x on which it's defined, it might have multiple possible solutions. So this terminology is very convenient. So we also think of a problem as a set of instance solution pairs. So if x lies in the domain of f, then we will say that x is an f instance. And for each f instance x, the set of f solutions to x is this set f of x, which is a subset of y. So for example, for ds, right, when I say an ds instance, I'm talking about an ill-founded linear ordering. And when I talk about the solutions to that ds instance, then I'm talking about all of the set of infinite descending sequences in that linear ordering. Okay, so that's how we talk about problems in a formal way. Now we need to talk about how we compare problems, right? Previously, we saw a couple of things which are some type of reductions between problems. So we need to give the reduction a formal definition here. And the notion that we'll focus on today is the notion of Weierach reducibility, also known as uniform reducibility. We say that a problem F is Weierach reducible to a problem G if there are computable functions phi and psi such that the following hold. So first of all, if we are given a name for an F instance, then we want to be able to apply phi and always get a name for a G instance. Okay, so I'm putting a picture here, which should be reminiscent of the picture we had on the first two slides of my talk. Secondly, we also want the following. So let's say we're given a name for a G solution to this G instance. So let's say Q, okay? Then we want to be able to go backwards, right? And this time, this is where we use this psi. So psi applied to this Q is going to give us an F solution to the original F instance P. And over here, there's something that's slightly different that hasn't come up, that didn't come up previously. Namely, we allow psi access to P. Okay, so this was not done in the previous slides, but this we allow in the definition anyway. I think it's a very natural thing to allow. Okay, so that's the definition of Weierach reducibility, right? F is Weierach reducible to G if there are these two functions which have these following properties. And we should think of it as a way of uniformly reducing F to G. In other words, given an instance of F, you can uniformly transform it into an instance of G such that given a solution, you can uniformly transform it back into a solution for the F instance. And just a point of terminology. So phi and psi, I will call them the forward and backward functionals respectively. Okay, so that concludes the very short introduction to Weierach reducibility. Now let's go back to the problems of DS and also choice on bare space. And let's talk a bit about what we know about their relationships. So this is, remember, so DS is the descending sequence, right? We're finding descending sequences, and choice on bare space is the one where we are finding paths in ill-founded trees. So the very first reduction that we had on the first slide, that is a Weierach reduction. So that shows that DS is Weierach reducible to choice on bare space. However, the second reduction that I showed you, the one that involves the Kleene-Brauer ordering, that is not a Weierach reduction for the following reason. So for the forward reduction, we applied the Kleene-Brauer ordering. That's perfectly fine, that's computable. However, when we were going backwards from the descending sequence in the Kleene-Brauer ordering to the path, we applied the limit, right? And that's not a computable operation. So it doesn't satisfy the definition of a Weierach reduction. So it's not a Weierach reduction. However, we can still phrase it in the framework of Weierach reducibility as follows. So this here is a bit of is an operation that we can do on problems, and this is called the compositional product. And what it does is it takes two problems and it forms a new problem out of it. And this new problem, this compositional product, captures what can be achieved by first applying G. So G is the one on the right, followed by some computation in between, and then applying F. Okay, so in this case, we are talking about this lim star ds, right? So this captures the power of what we can do if we apply ds first and then we apply lim, right? Remember, that's exactly what we did in this second reduction here. So essentially what we showed in the second slide is that choice on bare space is Weierach reducible to lim star ds. Now over here I wrote an equivalence. So I need to tell you also how you do the reduction the other way. And let me just say that, so it is known that both lim and ds reduce to choice on bare space. And also choice on bare space is actually closed under this product. So that's how we get the reduction in the other direction. Okay, so we are not going to talk about the compositional product again, but I just wanted to say that, okay, so even though on the face of it, we didn't obtain a Weierach reduction, right? We had some kind of reduction, but it's not a Weierach reduction, but it still can be phrased in these terms in the Weierach lattice. Now, so this raises the obvious question, namely, is choice on bare space Weierach equivalent to DS? And equivalently, because we already know that there is a reduction in one direction, so really the question is, does choice on bare space reduce to DS? So this is the main question, the motivating question of this talk, and we will answer it on the next slide. Okay. So here are our results. So we will show that choice on bare space is not reducible to DS. In fact, we will see that DS is actually quite weak in terms of uniform computational strength. And here's one of our results that implies what I said. Namely, what we did is we looked at the single valued problems that are Weierach reducible to DS. Okay, so a problem is single valued if every instance of the problem has a unique solution. Okay, for example, the problem lim that we saw. So that's the problem of given a convergence sequence in n to the n, compute its limit. So that is a single value problem, right? Because a convergence sequence has a unique limit. So that's one of these kinds of problems. And in fact, we showed that every single value problem which reduces to DS actually just reduces to lim. And this is an if and only if, because it's also not hard to show that lim itself reduces to DS. Okay, so another way to rephrase this result is the following expression. So over here, we are looking at all of the single value problems. These are the F0s, which are reducible to DS. And we are taking their soup in terms of, with regards to Weierach reducibility. and that soup is Weierach equivalent to lim. Okay. So later I will prove a result that is quite similar to this. So I'm not going to give the proof of this now, but first I should tell you how this actually implies the separation that I claimed in the title. So what this tells us is that, well, if we are able to find a single value problem that reduces to choice on bare space, but doesn't reduce to lim, right, then we will have a separation like this. And there are plenty of examples of such problems. So a corollary of this result is the following problems are not Weierach reducible to DS. Okay, so I'm not, I mean, some of these are not defined, but I want to talk about just some of them. First, let's talk about this guy here. So this guy here, this is unique choice on bare space. And this is the restriction of choice on bare space to essentially trees with a unique path. Okay, so this is much weaker than choice on bare space. For example, this unique path is always going to be hyperarithmetic, whereas you have trees with no hyperarithmetic path, right? So this is much weaker than choice on bare space, but well, it is single valued, and it definitely is not reducible to lim. Okay, so because of the theorem, this guy here is not reducible to DS, and so therefore choice on bare space is not reducible to DS. Let me talk a bit about, these guys over here. So another one that I want to talk about is ADS. So ADS stands for ascending descending sequence, and this is, as most of you know, this was intensively studied in reverse math because it's a consequence of Ramsey's theorem for pairs. And you might wonder, okay, well, is ADS Weierach reducible to DS, right? In some sense, DS is like the one-sided version of ADS, where we only care about descending sequences and we don't care about ascending sequences at all. And our results show that ADS is not reducible to DS. That doesn't follow immediately from this theorem because ADS is obviously not single valued, but there is a weaker problem, this so-called LPO prime, which is single valued and doesn't reduce to lim and does reduce to ADS. Okay, so this follows rather easily from this result. Okay, so I don't want to kind of go into details about, okay, what exactly is reducible and what exactly is not reducible, but suffice to say that this settles a lot of the questions about what is reducible to DS. And there is one open question that I want to highlight, namely Koenig's lemma. So KL, which corresponds to Koenig's lemma, is the problem of finding a path given a finally branching subtree of n to the less than n. And our results don't separate Koenig's lemma and DS. So that's an open question that we don't know how to answer at this point. Okay. So I mentioned earlier that I was going to give a proof of a theorem which is quite similar to this, and the reason is because the essence of the proof of this theorem actually tells us quite a bit more about how it gives us more insights into the strength of DS, like what exactly is reducible to DS and what is not. And this involves the what is called the first order part of DS. And what that means is that our techniques characterize the problems which have codomain the natural numbers and are Weierach reducible to DS. So in order to tell you the results, we have to give a definition. So here is a problem, a specific problem, which has codomain n. We call it pi on one bound. And what it does is that, okay, we are given a finite subset of the natural numbers, but we're only given a pi11 code for it. And then we have to produce a bound for this finite subset. In other words, we are trying to produce a number which is greater than all of the numbers in this set. Okay, so this is definitely, well, it's a problem with codomain n, right? Because the solution is just asking for a single number. And it's also not hard to see that it does reduce to ds. And what we showed is that, well, if you have codomain n and you reduce to ds, then actually you reduce to pi11 bound. So this soup over here is Weierach equivalent to pi11 bound. And this is a characterization, right, of exactly which problems have codomain n and are reducible to ds. So I will prove this theorem on the next slide. But before that, I just want to say that, so this is an example of a first order part of a problem, right? This soup over here is the first order part of ds. And this idea of a first order part was defined and studied recently by Zafarov, Solomon, and Yokoyama. And they defined this for just arbitrary problems f. So for any problem f, you can look at this soup, and they showed that, well, this soup is going to exist, and yeah. Okay. So now I want to tell you about the proof of this theorem, at least on the non-trivial half of it. And what do we have to show? So suppose we're given some arbitrary problem f, which has codomain natural numbers. And suppose we know that it is Weierach reducible to ds. Then our job is to show that it is Weierach reducible to pi11 bound. Okay, how do we do that? So we want to construct a Weierach reduction, right? So the first thing to do is, okay, we're given an instance of f, let's say p, and we want to define an instance of pi11 bound, which will come later. But first, let's think about this. So first, we can apply this Weierach reduction that's given to us, right? We are given a way of, given an instance of f, we know how to construct some ill-founded linear ordering, okay? And specifically, let's say we are at a certain stage S, then we can say that, okay, let's just look at a finite piece of the linear ordering that's going to be given by the forward functional. Now, if we just look at this finite piece of the linear ordering, we can just look at all of the descending sequences in this finite piece, right? All of these are going to be finite descending sequences, and we can run the backward functional on all of them. And for some of them, the backward functional is going to converge. And if it converges, since the codomain of f is the natural numbers, that means that this backward functional is going to give us a potential absolution. Okay. Obviously, like I say potential, right? Because we have no idea if this is actually correct, because we have no idea if these finite descending sequences are going to be extendable, right, to infinite descending sequence. But it's a potential solution, which we should keep in mind. Now, there is some point that I kind of glossed over in part 2, which is that, okay, such descending sequences might not exist at all, but in the long run, eventually they're going to exist, right? And if they exist, then we can attempt to guess an F solution by picking the rightmost descending sequence. Okay, well, what I mean is this, right? Let's say I gave you a bunch of finite descending sequences in a linear order. And I said, okay, pick the one which is most likely to extend to an infinite descending sequence. Then what you can do is you can pick the rightmost one, because if anything to the left is extendable, then well, if any finite descending sequence is extendable, then any finite descending sequence to its right is also going to be extendable. So our best guess is to pick the rightmost guy. And notice that all of this, steps 1, 2, 3 so far, all of this can be done computably, right? Okay, so where does power 1 bound come in? Well, now we use power 1 bound to figure out a stage such that this guy here, this fs over here, is extendable. So look at the set of S such that either fs is undefined, that can only happen for finitely many stages, or is not extendable. That can also only happen for finitely many stages. And that's the power 1 set with parameter p. So if we now apply power 1 bound to this set, that gives us some stage S such that this finite descending sequence fs is extendable. And then we just apply the backward functional that gives us a number, and that number is guaranteed to be an F solution to P. So that completes the proof. That shows that we've constructed a Weierach reduction from F to power 1 bound, right? First, we're given an F instance P, then we can define the power 1 set as in point number 4. And then to go back from a power 1 bound solution, that's the S here, we compute the Fs, and then we apply the backward functional that was given, which gives the F solution to P. Okay, so maybe you didn't follow every step in here, but let me just summarize the main ideas that's going on, right? The first main idea is that if you're given finite pieces of possible, like if you're given finite descending sequences, okay, in a linear order, then we can computably guess which one is most likely to be extendable to an infinite descending sequence. So that's really the main idea that's going on here. And secondly, why do we restrict the codomain to the natural numbers? That's so that once the backward functional converges, then we know that it's going to give us a solution, right? If this was something more complicated like a real, right, then we are not going to get it at any finite stage of the computation. Okay, so that's the sketch of the proof. Now I want to talk a little bit more about power 1 bound itself, because actually it has been studied by other people. So power 1 bound is actually can be thought of as a sigma 1 choice principle. So this is one of the sigma 1 choice principles for the natural numbers. We are given a sigma 1 code for a non-empty subset of n, and we are asked to choose an element of this sigma 1 set. There is a restriction of this problem where instead of looking at all of the non-empty subsets of n, right, you restrict your instances to just the cofinite subsets of n. Okay, and that's indicated here by the COF. Now, it's not hard to see that power 1 bound is actually Weierach equivalent to this cofinite sigma 1 choice. And these principles were studied by Angles, Doriak, and Kihara. And here is one of their many results. They showed that this cofinite choice is actually strictly weaker than this sigma 1 choice itself. And the way they did that is that they took the what is called the infinite parallelization of both of these principles, and they separated the things here, which implies the separation here. So I didn't define the infinite parallelization. Let me just say it real quick. So the infinite parallelization of a problem, instead of solving one instance of the problem, you have to solve a whole sequence of instances of the problem. Okay, so you're given a sequence of instances and you have to solve all of them. Okay, so why do I bring this up? I mean, like, what does this have to do with DS at all? The reason is that this sigma 1 choice on the natural numbers, it's easy to see that this is actually the first order part of choice on bare space. So in this separation here, what we have on the right-hand side is the first order part of choice on bare space. The left-hand side is the first order part of DS. So this tells us that DS and choice on bare space can be separated by considering their first order parts. Okay, so that's one way of thinking about how we can separate two problems. We can think about, okay, can we separate their first order parts? And this is what is being done here. In fact, our results imply something that's somewhat stronger, because actually we found a single value problem with codomain 2, which separates the two. Okay, so this is, I mean, far more restrictive than just codomain n, right? So our results actually do a bit more than this, but I just wanted to mention this as a, like a general strategy that one can try. Okay, so in the remainder of the talk, I want to talk about another result in this paper by Angles-Dorec and Kihara, which concerns this parallelization of sigma 1 choice. So earlier, Kihara, Makona, and Polly asked if this guy is strictly below choice on bare space. And Angles-Dorec and Kihara showed that, yes, they are separate. And what we're interested in here is the technique that they did it. So they considered this other problem, ATR2, which reduces to choice on bare space. And they show that this guy does not reduce to this parallelization. And the way that they showed this separation is using a pair of inseparable pi11 sets. So what we're going to do is we will extend their techniques to prove a stronger result about the strengthening of DS. Okay, so that's the plan for the next couple of slides. But before that, I need to define a whole bunch of things, right? So first of all, I should tell you what ATR2 is. So ATR2 is the following problem. It's a two-sided version of a problem that in some sense corresponds to ATR in reverse math. So in ATR, in reverse math, you say, okay, for any well ordering, there's a jump hierarchy on the well ordering. And now I'm saying that, okay, let's broaden the domain. So instead of restricting it to just well orderings, let's look at all linear orderings. So now we're given a linear ordering L, which doesn't have to be well ordered. And we ask for one of two things. So you can either produce an infinite descending sequence in the ordering, or you can produce a jump hierarchy. And there is a single bit, you can put like a single bit at the beginning, which indicates which type of solution you produce. Okay, so that's ATR2, and it's easy to see that this reduces to choice on bare space. And I just want to mention this, that going forward, I will mostly just talk about ATR2 restricted to computable linear orderings, because that's all that is needed for this separation. Okay, so with this, now I can state our result. So what's the relationship between ATR2 and DS? Okay, so our results, our previous results already imply that ATR2 does not reduce to DS, but actually much more is true. So let's consider the following strengthening of DS, where instead of being given a linear ordering, we are given a sigma 1 code for a linear ordering. Okay, so obviously DS reduces to this, and well, it's easy to see that this is actually much stronger than DS itself. Nonetheless, ATR2, we're going to show that ATR2 does not reduce to this guy, which implies that this guy is still strictly below choice on bare space. Okay, so earlier in the talk, right, I said that DS is strictly reducible to choice on bare space, and now this is a strengthening of that result. And this result also strengthens the result by Angles-Dorec and Kihara, because this parallelization reduces to DS. But okay, that's kind of besides the point. Now, how do we interpret this result here? So one way I think about this is think about, say, a loosening of the notion of Weierach reducibility. Okay, so in Weierach reducibility, we have the forward and backward functionals both have to be computable, right? So what if you say that, okay, the backward functional still has to be computable, but the forward functional is allowed to be sigma 1, 1. Okay, so that's a much more generous notion of reducibility. Even then, choice on bare space still does not reduce to DS, even under this looser notion of reduction. Okay, that's because of this sigma 1, 1 thing here, right? So that's how I would interpret this result. And I want to compare this to what we saw near the beginning, which talks about the backward functional, right? In the beginning, we saw that if you do this Kleene-Brouwer thing, as long as you allow the backward functional to be limit computable, then you do get a reduction from choice on bare space to DS. Okay, so just a little bit of power, extra power in the backward functional allows you to do this. But even if you strengthen the forward functional by a lot, you still cannot get this reduction. Okay, let's talk about the ideas behind this proof. And in order to introduce the ideas, I need to tell you more about ATR2 and these inseparable pi-1-1 sets. So what makes ATR2 interesting is that you can think of it as sort of a union of the following two problems. So one problem is DS, right? Which given this ill-founded linear ordering, you produce a descending sequence. But also, well, if you're given a linear ordering which supports a jump hierarchy, you can produce a jump hierarchy, right? So ATR2 is kind of the union of these two because you're allowed to produce a solution to either one of them. And in some sense, what makes ATR2 hard is that it's difficult to decide which of these two problems you want to try to solve. Okay, because given a linear ordering, it's hard to figure out whether it's well-founded, right, as is well known. So it's well known that the set of indices of ill-founded linear orderings is complete, sigma 1, 1 complete. And also for the jump hierarchies, Harrington showed that the set of indices of linear orderings which support a jump hierarchy is also sigma 1, 1 complete. Okay, so if you were to try to solve ATR2, right, you might think, okay, well, let me figure out whether it's well-founded. Well, okay, that's hard. Well, let me try to figure out whether it supports a jump hierarchy. That's hard too. So you can't really get very far by this approach. And after studying Harrington's proof, I realized that it actually essentially proved a stronger result, right, which says that any sigma 1, 1 set which separates these two sets of indices must be sigma 1, 1 complete. So WF is the indices for well-founded linear orderings, and HDS is the indices for linear orderings with hyperarithmetic descending sequences. So these two sets are inseparable pi-1-1 sets. Okay, in the sense that, well, any sigma 1, 1 set that separates them has to be complete. In particular, there is no delta 1, 1 set that separates these two guys. Okay, so so let me just quickly mention that this generalizes Harrington's result because you can look at the sigma 1, 1 set of indices of linear orderings which support a jump hierarchy. That obviously contains WF because every well-ordering supports a jump hierarchy, and it is disjoint from HDS. That's a result of Friedman. So Friedman showed that if you have a hype descending sequence, then you do not support a jump hierarchy. Okay, so for the separations that we're going to do in a Weierach lattice, actually we just need a corollary of this, which I will tell you. So here's the theorem repeated from the previous slide, and here's an immediate corollary. By sigma 1, 1 separation, we know that these two pi-1-1 sets cannot be separated by disjoint sigma 1, 1 sets. Okay, so you cannot find a sigma 1 set that contains WF and another sigma 1 set that contains HDS and are like such that the two sigma 1 sets are disjoint. That's not allowed. Okay, so this is the corollary that they use to prove this reduction, and we will use the same corollary to prove to prove this separation, and we will also use the same corollary. Okay, so how do we do this? So let's suppose that there is a Weierach reduction from ATR2 to this sigma 11 DS. What we will construct two disjoint sigma 1 sets that separate WF and HDS. Okay, and these two sigma 1 sets will be derived from this Weierach reduction in some way. So first of all, let's give some names. So for each computable linear ordering LE, the forward functional that's given to us produces a sigma 11 code for some ill-founded linear ordering. Now, what does the backward functional do? That's not so obvious, right? So the issue here is that, well, the backward functional takes in some descending sequence in this phi of LE. And it might produce descending sequences in LE. It might produce jump hierarchies on LE, right? That's for the same E, both of these options could happen depending on which descending sequence you get. Now, however, there is a property of descending sequences that we can exploit. In some sense, descending sequences are sort of homogeneous. I don't mean this in a technical sense. What I really mean is that, okay, if you have an infinite descending sequence, you can essentially swap out an initial segment of it, and it will still be an infinite descending sequence. So exploiting this kind of property, we can prove the following lemma, which says that for each E, either of these two is Mushnick reducible to this guy. So just to remind you what Mushnick reducible is, right? This is the non-uniform kind of reducibility. This is saying that, okay, either given any descending sequence here, you can compute a descending sequence here, possibly non-uniformly, or given a descending sequence here, you can compute a jump hierarchy, again, possibly non-uniformly. Okay, so what is this lemma for? Well, that tells us how to construct the sigma 11 sets, namely consider the two sigma 11 sets below. So the first one is the set of all E so that DS is not Mushnick reducible to this. And the second one is the set of all E such that this jump hierarchy is not Mushnick reducible to this. The lemma tells us that these two sets on the right are disjoint. And just by the definition of Mushnick reducibility and the definability of these guys, these sets are sigma 11. And furthermore, well, if you are well-founded, if LE is well-founded, then this is the empty set. So of course, the empty set is not Mushnick reducible to anything. Similarly, by Friedman's result, if you have a hyperarithmetic descending sequence, then you don't have a jump hierarchy. So this is the empty set. So again, HDS is going to be a subset of this set. So this construction now contradicts the corollary on the previous slide, which completes the proof. And that's all I have for today. Thank you for your attention.
Yeah, many thanks for your talk. So I think we have plenty of time for some questions. Are there any questions?
So Jun Le?
Yeah.
So you mentioned that, well, the Koenig's lemma was reducible to DS.
Yeah.
As being open, but does that mean you know about weak Koenig's lemma?
Yes. So weak Koenig's lemma is reducible to lim, which is reducible to DS.
It's reducible to what? To lim. Right. Good.
Yeah.
Right. Good point. Yes.
Yeah.
But if I may add something to that question, I think the question was whether Königs lemma is reducible to DS, not weak-Königs lemma, isn't it?
Yeah, but Richard was asking about like whether I knew anything about weak-Königs lemma.
Ah, okay. Okay.
So I concluded that he knew that weak Königs lemma was,
Right.
Okay.
but I didn't see the proof. So now I see the proof.
Right. Yeah. Yeah. It would, in order to contemplate this problem properly, it would be helpful to have like a zoo, right, of all of the things which I refrain from drawing. But yeah.
So do you have any conjecture regarding the Königs lemma question?
Well, I guess the usual conjecture is that we tried to reduce it and we couldn't. So probably the conjecture is no. Yeah, but at this point, we don't have a real reason to believe either way, I think. Yeah.
So are there any other questions? So if someone just would like to ask a question, please do not forget to unmute your microphone.
I should probably know that, but would unique choice suffice to translate a sigma one code for the linear order to a computable code for a linear order with roughly the same unique sequences? So is it true that sigma 1 ds is below ds star unique choice on their space?
Not that I know of. Yeah. I mean, yeah, no, if that were true, we should definitely put that in a paper. Yeah. Yeah.
So I had a question about the notation, the meaning. When you say things like sigma 1 ds or bounded pi 1,
yeah,
and you're talking about the indices. So are you allowing, at one point you allowed a parameter?
Yes, so I am allowing parameters.
Are you, you're always allowing parameters?
Yes.
Okay, so when you write sigma 1 ds, you mean boldface in some way?
Yeah. Yep.
I wasn't sure until you had the parameter appear once. Okay.
Yeah, that's I contemplated like putting boldface all over the place. I guess I should. Yeah.
That's okay. So, but then is there some uniformity issue in terms of how the parameter is handled when this comes up?
Not really, right? Well, at least not in the reductions that we looked at. For example, if we go back to the
I mean, every set is pi 1 in some parameter, right? Every set of natural numbers is pi 1 in some parameter.
Well, yeah. Well, I mean, it's over here, we're actually only talking about finite sets, even, right?
Yeah.
For pi 1 bound, yeah. So.
Right, but the sigma 1 is not.
I mean, the input to pi 1 bound is essentially some index e and a parameter p, such that sort of the e's pi 1 set relative to p happens to be finite, and that's the one that we want to.
Okay, so the answer is yes.
The bound for.
There is a uniformity in the parameter.
Yeah.
You're thinking of that as part of that was the okay. Thank you.
Okay, yeah, I wasn't sure if that was your question.
Good.
Yeah.
Yeah, that was.
Yeah, and the same kind of thing is happening for the sigma 1 ds.
Right. So then the same. Yeah.
Yeah.
Okay, so are there any other questions?